Way back in 1969, a single academic paper dropped a radical idea that would, honestly, change how we think about software forever. It tried to answer a question that haunted the early days of computing, a question we are absolutely still grappling with today.
I mean, just think about it for a second. Software runs our entire world, right? From the phone in your pocket to the power grid itself. But how do you prove with stone-cold mathematical certainty that a piece of code will do exactly what you want it to and nothing else? This was the massive problem facing the pioneers of computing.
And the stakes, well, they couldn't be higher. In the paper we're diving into today, the computer scientist C.A.R. Hoare put the potential cost of software bugs in these really chilling terms. This wasn't some academic thought experiment. It was, quite literally, a matter of life and death. So here's our game plan. First, we're going to look at just how bad the bug problem was. Then we'll get into the revolutionary logic that was proposed as a solution. We'll learn the actual language of proof, ask if code can really be proven correct, and finally, see what the ultimate payoff of this whole idea was supposed to be.
All right, first up, the high cost of bugs. Before you can really appreciate the solution, you gotta understand the scale of the problem. By the late 60s, software was getting more and more complex, and the failures, well, they were getting catastrophic.
You know, the standard way to do things was something called program testing. You'd write your code, and then you'd just try it out. You'd throw a bunch of different inputs at it and see if it broke. But here's the huge catch. Testing can show you that bugs are there, but it can never, ever prove that they're not there. You're always worried that you just missed that one weird input that'll bring the whole thing down.
And this number, wow, it's just staggering. Hoare pointed out in his paper that for a lot of big projects, over 2/3 of the entire budget was just spent on testing and fixing bugs. Just think about that for a second. Most of the effort wasn't even in creating something new. It was just in patching up the broken stuff. It was wildly inefficient, super expensive, and you still couldn't be sure it would work.
So clearly, a totally new approach was needed. And this brings us to a revolution in thinking, an idea to take programming from a kind of trial and error craft and turn it into a real science.
In this paper, C.A.R. Hoare basically asked, what if we're looking at this all wrong? He wanted to take the same kind of rigorous, logical thinking that mathematicians have used for centuries and apply it to the messy world of computer code. His central analogy was, believe it or not, geometry. You remember from school, right? You start with a few basic, undeniable truths called axioms, like a straight line is the shortest path between 2 points. And from those simple rules, you use logic to prove incredibly complex things. Hoare's question was simple. Why can't we do that for programs?
And this is the fundamental shift. It's moving away from testing, which is really just bug hunting. It can only find evidence of errors, and moving towards proof, which provides logical, mathematical certainty. It's the difference between saying, well, I haven't found a bug yet, and being able to declare, I have proven that no bug of this kind can possibly exist. That's a game changer.
Okay, so how in the world does this actually work? To build these proofs, Hoare knew he needed a brand new kind of language, a formal way to reason about what code is actually doing. And this is the heart of his entire system. It's called a Hoare triple. I know PQR looks a little cryptic, but the idea behind it is incredibly elegant and actually pretty simple. Let's just break it down. P is the precondition. That's just a statement about what the world looks like before you run the code. Q is the program, the code itself. And R is the postcondition. That's what you claim is going to be true after the code has done its thing. So really, you should think of it like a logical contract. The entire statement, P, Q, R, is a promise. It says, if you give me a situation where P is true, and then I run my code Q, I absolutely positively guarantee that afterward, R will be true. It's a formal way of talking about cause and effect in software. But how do you build a proof like this? Well, you have to start on solid ground, with axioms. Axioms are just the unbreakable, self-evident rules of your little programming world. Things like what actually happens when you assign a value to a variable, or the precise definition of a while loop. They are the bedrock you build everything else on top of. And this is a brilliant example from the paper of why defining your axioms is so critical. Imagine a tiny computer that can only hold numbers from 0 to 3. What's 2 plus 2? Well, it depends on the rules. Under a strict axiom, the answer overflows, so it just doesn't exist. With a firm boundary, it hits the max and stops, so the answer is 3. And in modulo arithmetic, it wraps around, so the answer is 0. You see? You can't prove anything until you've defined the fundamental physics of the universe your program lives in.
All right, so we have the building blocks. We've got the axioms and the Hoare triple. So the big question is, can we actually put it all together to prove that a real program is correct?
And the answer, amazingly, was yes. Hoare's paper shows that by chaining these logical statements together, you can build a formal proof for an entire program. He actually does it. He provides a full and, very tedious proof for a division program. He proves step by logical step that it will correctly calculate the quotient and remainder for any two positive numbers.
Now, here's the most important part. The goal wasn't just to make one long, boring proof. The goal was to prove that it was possible. For the first time, Hoare showed that you could talk about computer programs with the same formal certainty as a math theorem. He was turning computer programming into a potential branch of mathematics.
Now, this is all fascinating stuff, theoretically, but what are the practical benefits? Why go through all this trouble of proving programs? Well, Hoare laid out 3 huge payoffs. The first and most obvious is reliability. A proof is a rock-solid guarantee. It's not a hope, it's a fact. Second is documentation. Those preconditions and postconditions, the before and after states, that's the most accurate user manual you could ever ask for. And third, compatibility. If you base your proof on general rules, not a specific machine, then your program is proven to work on any computer that follows those same rules.
It's honestly hard to overstate the impact of this one paper from 1969. It launched the entire field of formal software verification. The tools and techniques that we use today to check the code in airplanes, in medical devices, in our financial systems, they all trace their family tree right back to these ideas.
And that all leads us to one last fascinating question. If the theory for proving software has been around for over 50 years, why do our apps still crash? The answer really lies in the mind-boggling scale and complexity of modern software, and the sheer difficulty of applying these tedious proofs to millions of lines of code. The dream of perfectly provable software is still out there, but reality, as it turns out, is a lot more complicated. Thanks for joining me on this explainer.